All right, we're going to be looking at one of our more fundamental sections today, um, dealing with factoring, but not just quadratics anymore. Now we're going to be looking at other polynomials as well. We're going to be using what we do in this section for quite a while. So we kind of break things up as you look at this front sheet by the number of terms, whether there's 2 or 3 or 4. Um, there are all sorts of patterns involved in factoring, but especially if there are 2 terms. Then we are going to definitely want to look for some of the patterns that we have listed here. No matter what you do, no matter how many terms, no matter how you're going to factor, always try to factor out a GCF first. Pull out a GCF, that's always going to make things a little bit easier. First thing we're going to look at here is the difference of squares. Well, that's one that we've done before. Oops, difference of squares. So we'll just put that down. Not going to talk much about it here because we've done that before. New to you now is factoring the difference and the sum of cubes. The difference of cubes, when you have one thing cubed minus another thing cubed, you have to identify what those things are. So identify what A and B are here, and then put them into this pattern. You have a binomial that is the difference of A and B, and then a trinomial that looks like this. Don't need that 2 there. The sum of cubes looks almost identical to this pattern, except when we had the difference, we put a difference in the binomial, and then we changed it there in our binomial became a plus. In the sum of cubes, that's a sum in our binomial. And then in our trinomial that we have here, our quadratic trinomial, we're going to have a difference then. That last thing is always square, or excuse me, always positive because we're squaring b to get it. So b squared is always going to be a positive value. One thing I'll mention again later, but I'm going to say right now, these 2 trinomials, these guys here, are never, ever factorable. So if you're solving, you're probably going to have to use the quadratic formula. The sum of squares, we don't really use that for factoring, but it's related to the difference of squares. So we're just going to remind ourselves that, actually I'll put it the way we use it more often is when we have 2 conjugates being multiplied together, a plus bi, a minus bi. That conjugate pattern leads to the sum of squares, a squared plus b squared. All right, let's move on to when we have a 3-term quadratic. So the first thing we're going to look at is when you have an a value that is 1, your leading coefficient is 1. And in this example here, you might think, well, it's not 1, it's a 3. But look at, we got a 3 that we can factor out here. And since we're factoring, we're going to leave it there. There we go. And now we have a trinomial that has a leading coefficient of 1. So we're going to be able to factor this guy here. I mean, they're not always factorable. This one is. 2 factors of 8 that add to -2. 4 and 2, and you want the 4 to be negative so that they add. Remember, this product and this product have to add to the -2. That's right here. Okay. A little more work when there's a leading coefficient that's not 1 and you can't pull out a GCF. So here we're going to have to do a little bit of guess and check. So again, remember, it's this product and this product we want to add up to that 1x that's in the middle. So some factors of -10 are obviously 5 and 2, 10 and 1. I'm going to put the 5 here and the 1 and the 2 there. Try that out. Look, I have 4x here as my product, and I have 5x there. If I make that 5 negative, this will add up to that. Sorry, if I make the 5 positive, screwed that all up now. This will add up to that 1 that we have in the middle there. We have 5x and -4x. So that's going to be our final form here. I'm just going to write this a little bit nicer. One thing that we haven't touched on much, as you're guessing and checking in this one, I'm just going to throw this out there. If you're thinking about 5 and 2, you know the 2 cannot go there because this would have a GCF of 2 then. And since we didn't have a GCF to begin with, there's no way that this thing can have a GCF of 2. So you pretty much know that the 5's got to go there and the 2 has to go there. And then it's just, how do I get that positive x in the middle? All right, if you have still 3 terms, but you have a degree higher than 2, like a quartic trinomial. Remember, quartic means 4th degree. So here's an example of what that would look like. We're going to do one of those on the next page, so I'm going to wait on that, but I just want you to see what it looks like here. Okay? All right, last one. This is something that you might have just touched on a little bit in Algebra 1, and that's grouping. Grouping is something that we'll perform on cubic polynomials of 4 terms, as long as they're groupable, and you'll see what grouping is. All right? Right here, we're going to do a quick grouping example. What you're looking for, and we call it grouping because we're kind of in our heads grouping these terms together like this. What you're looking for is a GCF of the first 2 terms. Looks like I can pull an x squared out of those. So it's going to look like this if I pull it just out of those first 2 terms. I'd have 2x plus 1. Now, the whole idea behind grouping is if I can pull a GCF out of this one and still have that 2x plus 1 again right here, that means it's groupable. So if you notice here, I can pull a minus 2 or a negative 2 out of that second group. Not a negative 2, sorry, a negative 8 out of that second group. And if I pull that out of that second group, I'm left with the same binomial here and here. That's going to be one of my factors. In fact, what I kind of want to do now is pull that thing out as a GCF. And I'd be left with those 2 GCFs that I pulled out originally, x squared minus 8. So basically, the thing that repeats is one of your factors, and the things you pull out represent your other factor. Now you're going to find out when you are doing grouping that a lot of cases one of these will still be factorable, okay? Or it could be factorable. So if you can keep factoring, keep factoring. For example, if this were a 9 right there, we could call this x plus 3, x minus 3, okay? So you keep factoring, and then obviously you'd bring this down. You keep factoring if possible. With this one, it looks like we're done right there. This is what this would factor to. All right, now we're going to look closer at those quartic trinomials. So what I put here is if you can factor this guy, you can factor this guy. All right, so this x squared minus 13x plus 36, if I ask you to factor that, you've got 9 and 4. Both are going to have to be negative. So that's what that would factor to. This guy, we're going to pretty much factor the same way, except since my first term is x to the 4th, I'm going to need x squared and x squared there to begin with. Still going to be minus 9. It's still going to be minus 4, because those will add up to that negative 13x squared if I do that, those 2 products right there and add them together. What do you notice about this one? Both of these are still factorable. We have x plus 3, x minus 3, and then x minus or x plus 2, x minus 2. So that is fully factored. You want to keep factoring as long as you can factor. That is completely factored. And we're going to use that now. We're going to look at, if we turn this into a function, what that graph would look like. Our zeros are going to be the same as our zeros from our factors. So we're going to have zeros of, actually I'm going to write this up here because this is talking about this function. This function has zeros of negative 3, negative 2, 2, and then 3. I just put them in order there. You could go plus minus 2, plus minus 3 if you're listing it out. Those are the zeros of that quartic trinomial. So The zeros, remember, are x-intercepts. So we know that this thing is going to go through those points. We've got from that first guy, -3 and 3. And then we have -2 and 2. This sketch does not need to be to scale. And then to do this sketch, you need to think about end behavior. This is positive and it's quartic, or it's even. So since this is positive, or I should say, since the leading coefficient is positive, and since this is even, our end behavior we know is going to look something like this. It's going to go up as we go left, and it's going to go up as we go right. We also know that it has a y-intercept of 36, so this is not to scale at all. I'm just going to say, hey, here's 36. But this thing we know is going to go up this way, and then I'm just going to come through, go through my zeros, and everything should work together. Everything should work together. It should go through your zeros, it should go through the correct y-intercept, and it should have the correct end behavior. That's a pretty good sketch of that graph. If you can dodge a wrench, you know the rest. All right. Actually, before we get too far here, I did actually graph that thing, and so our sketch is pretty good. You know, obviously, I had to change the scale of the axes a little bit, but it's going through -3, -2, 2, and 3 here, and then there's its y-intercept of 36, and our end behavior matches as well. All right, now we're going to solve a quartic trinomial equation by factoring. So let's take a look at what this would factor to. We've got x squared and x squared. This is equal to 0. Now in this case, if I would have a GCF in this problem that I could pull out, I would divide by it because we're solving, and we could divide by numerical GCFs when we're solving, as long as I don't divide by a variable, because then we lose answers. But this is good. So any factors of 32 that add to 14, I think 8 and 4 is not going to work, but 16 and 2 will work. I need the 16 to be negative. So I could factor this further, or I could just go ahead and set this equal to 0 right away. Use our zero product property, set these equal to 0. Oops, I forgot to set that one equal to 0. And then if I solve these, just don't forget when you take the square root, add 16. I will take an extra step to show that. I'm going to add 16 over. I'm going to take the square root. And this one, I'm going to add that 2 over. Take the square root. We're going to leave this exact. I don't know what the square root of 2 is, so I'm going to leave it as the square root of 2. Oh, I just realized something here. This is positive, which means this is negative, which means we're going to have imaginary solutions here. I still want to give those as answers. They are solutions. They're just not going to be x-intercepts on our graph. So the only x-intercepts we're going to have on our graph are the positive and -4, but not our imaginary solutions here. So on our graph, I'm just going to put -4, +4. It's got a y-intercept of -32. We're positive and even again, so it's going to come through these guys, go down through -32. How do we know that it does this funky thing down here? Well, because of those imaginary solutions. Okay, oh, this is -32 right here where it's crossing the y-axis. Okay, and just to verify that, there's the actual graph of that thing, and it has the same x-intercepts, same y-intercept, end behavior, looking good. The next one we're going to look at here is a 4-term cubic polynomial. Remember, we treat these, or we factor these by grouping. So another example of that. We're looking at a GCF right there. Looks like I could pull out an x squared. That would leave me with x plus 2. I pull out a GCF there, looks like I pull out a negative 16. And that would leave me with, again, x plus 2. And so one of my factors is going to be the x squared minus 16. And my other factor is going to be that binomial that repeated, x plus 2. There's factoring by grouping. Okay, so there we factored it almost completely. We just need to keep factoring the difference of squares that we see right there. So this guy would have, if we look at its factored form here, I'm just going to rewrite it right here. And its zeros are, if we use our zero product property, positive and negative 4, and then negative 2 from that last one. We're going to sketch a graph of this. It has 3 real zeros. So there's no imaginary zeros of this thing. They're all real because it's an x cubed. Now this one's got end behavior. If it's positive and odd, it's going to look something like that. So we're going to go negative 4, negative 2, and 4. Y-intercept is negative 32. So let's think about what this is going to look like. We know the end behavior we said is going to look like this. So we're going to have to start down here, come through our 2 zeros here, then it's going to go down through negative 32, so this is not the scale. There's the graph of this guy. I have it, the actual graph right there. I use Desmos for this. Desmos makes it really easy if we're interested in finding these local, this is a local max, and this guy here is a local minimum. Desmos makes it pretty easy to find those. You can find those on your TIs as well. Just takes a little bit more work on your calculator menu. But we have an idea of what that graph looks like as well. All right, we're going to put our difference in sum of cubes patterns down here again from our first page. So we've got a minus b is our binomial. Remember, if it's a minus, then we have minus in our binomial, and then this guy is going to be plus right there. And then if it's a sum of cubes, we're going to have addition within our binomial. And then this first sign here is going to be subtraction. Last one is always positive. All right, so first thing you want to do is look for a GCF. I don't see a GCF there. 9, 3, they don't go into 64. So these are both in cube. They're both things that are cubed. This could be considered to be 3x cubed, and the next one could be considered to be 4 cubed. So a is 3x, and b is 4. You don't have to worry about that negative there. That's going to be part of the pattern that we write out. So writing our pattern, we have a minus, because of the minus there, b, and then be careful here. A squared, you got to square that whole thing, is going to be 9x squared. This is going to be addition, because that always switches signs. Then I multiply the two things together, get 12x, and then I have to square b. So this thing is totally factored. Remember, this guy is never ever factorable. Don't waste your time trying to factor that. As long as you factor correctly with the difference of cubes, you're done. You got another one here. Maybe you notice right away, neither 16 or 2 are perfect cubes, but that's because we can actually pull a 2 out first. And we're going to make sure to put that in our final answer then, the 2 that we pulled out. So a, what we would cube to get that is 2x. B is 1, because you cube 1 to get 1. So we're going to have a minus b, or excuse me, a plus b, because it's the sum of cubes. So 2x plus 1. A squared would be 4x squared, minus the product of those two things, 2x times 1, and then plus b squared. Totally factored. Don't forget that 2 in your final answer if you're factoring. All right, now we're going to solve using the sum or difference of cubes. We're going to use that same guy that we just had, which we already factored this. So we know it's 2x plus 1, or 2 times x plus 1, and then 4x squared minus 2x plus 1. This all equals 0. Well, we can get rid of that. We can get rid of that because we're solving, so we can divide the whole thing by 2. We don't really need that anymore for the solving piece of this. So we're going to set each of these equal to 0. Okay, it wants us to find all the roots. So we have negative 1 from that guy. This guy, we're probably going to have to use the quadratic formula. You could complete the square if you want. Have fun at that. I'm going to use the quadratic formula here. I'm going to find my b squared minus 4ac first, my square root of my discriminant. So b squared would be negative 2 squared, which is 4, minus 4 times a times c. A is 4, and c is 1. Okay, make sure you're looking at the numbers there when you're using the quadratic formula. So if I simplify this, I get 4 minus 16, which is negative 12. 12 has a 4 and a 3 in it. I'm going to put the negative with the 4 so that I can simplify this to 2i square roots of 3. So I'm going to put that into my quadratic formula here. Negative b would be 2, and we have plus or minus 2i square roots of 3 all over 2a, which would be 8. Let's separate. So we have 2/8 and simplify, which is 1/4. Plus or minus, when I separate, I can simplify between that 2 and that 8 and call it 1/4 again. And I'm going to put that I back here. All right, so our roots of this equation are negative 1. That's the real root that we got. And then we got 2 imaginary roots. Imaginary roots always come in pairs. They always come in conjugate pairs. So that represents 2 solutions to this, even though they're not real. So we have 1, 2, 3 solutions of this thing, which makes sense because it's a cubic polynomial. So it should have 3 total solutions. It just happens that 2 of them are imaginary. So we really don't have much to go off of here if we want to sketch a graph of this. Take a second, put whatever you think your best guess is as what the graph of this looks like. We know that it has I'll give you a second to do that, or pause the video and do that. And then we're just going to put the actual graph here. We know that it has a real 0 at negative 1, and it has a y-intercept at 2. We can finally put one here, that's the scale. And it's got odd positive end behavior. This thing's going to end up looking something like this. And look at the actual graph here. I have it somewhere. There it is right there. Kind of hard to see. Here is the x-axis here. Here's the y-axis. Okay. There's our y-intercept of 2. There's our oh shoot. I just realized something. Don't you love it when you get all the way through a video and you make a mistake? So I'm sure you noticed this already before I did. It's a very minor part of what I did up here. I didn't copy this over correctly. That's 2x plus 1. So that should have been a 2 right there. Sorry about that. 2x plus 1. Our x would equal negative 1/2 here if we subtracted 1 and divided by 2. Our roots are negative 1/2 in those 2 imaginary roots. And that means our 0 right there is actually negative 1/2. I'm sure you guys all noticed that a long time ago. Sorry about that. So that is why we're crossing through negative 1/2 right there. All right, our last example here. When you're asked to solve by graphing, that means that you're going to be using your graphing calculator. Okay, so we got a little practice with our graphing calculator here. In class, I'll do it on my graphing calculator and make sure you guys feel comfortable with that. Some of the graphs I have here I did on Desmos. But there's two methods to do this. Here's the equation that we're solving. One method is to get this set equal to 0 and then find the x-intercepts. Okay? To solve by graphing, you can only find the real zeros, which would be the x-intercepts of the graph. So if we want to get this set equal to 0, we would subtract, I would subtract the 4x squared over and the 3x over, and now I've got this equal to 0. And I'm going to graph this function. Okay, so you don't have to rewrite it again, but if you want to consider this to be f of x equals that same expression, now we're going to graph that thing. Notice that there's no constant term here. Okay, in other words, the constant is 0. That means the y-intercept is 0. Well, that's because we could pull out an x if we were factoring this. We could pull out an x, and one of our zeros would actually be 0. We know this is going to cross through the origin, because that's the y-intercept and one of the x-intercepts. Okay, so that's kind of something that we can get even before we graph it on our graphing calculator. So what you're going to do is you're going to go to your graphing calculator, and you're going to type this in, 4x cubed minus 4x squared minus 3, 4x cubed. Get out of that exponent, and then minus 4x squared minus 3x. And I'm going to zoom into my standard window. So I'm going to hit zoom 6. Take a look at what this graph looks like. Okay, and then in order to find those zeros, you might want to zoom in a little bit more. I'm going to just change my window to go from -5 to 5 on the x-axis. And then take a look at this again. I just want to get closer to those zeros. All right, so now we can more easily find this 0 here and this 0 here. Looks like it's going through 0, but we can get those zeros by going second trace, not second trace, excuse me. Yeah, that's what we want. I just didn't do it correctly. Second trace would take me to this menu. We want to find a 0, so we want number 2. And then this is the kind where it asks you for the left bound and the right bound. So I'm going to focus on this 0 right there. I just have to get to the left of it and hit enter. And then I got to get to the right of it. It's asking me for a right bound now, so I just got to get to the right of that 0 and hit enter. And just make sure that where it's crossing the x-axis is between those lines or between these two arrows up here. It asks you to give a little guess. So I'm going to get a little bit closer and just hit enter. And it says one of our zeros is -1/2, 0. So let's do a sketch of this here. One of our zeros is -1/2. We also had 0. And I'm going to go ahead and find this other 0 right here. I'm going to go second trace again. I want to find a 0, number 2. I got to get a little bit closer here. So make sure you are to the left of that 0. Okay, so I got to be to the left of right there, which I am. I'm going to hit enter. Now I'm going to get to the right of that 0. I'm going to hit enter. Make sure that your x-intercept is somewhere between those lines. Get a little bit closer and hit enter. Our third 0 is 1.5 or 3/2. So that's our third 0 there is 1.5 or 3/2. So I'm just going to do a little sketch here. We always sketch our graphs if we're using a graph to solve. So it came through like this. It had the exact end behavior that we thought it would, because it's an odd degree and it's a positive leading coefficient. So our zeros are -1/2, 0, and 3/2. So that's one method of doing this. Get your equation equal to 0 and find the x-intercepts. The second method is going to be to use two graphs or two curves and find the intersections of those two curves. We are looking for the x value of the intersections. Look for the x values of the intersections. Okay, so I'm going to graph both of these. I'm going to graph this guy here. I have a different color. I'm going to graph that guy, and I'm going to graph that guy. So I'm going to put this in as y sub 1. I'm going to put this in as y sub 2. So let's go ahead and do that. Go back to your y equals. I'm going to clear this guy out and just type in 4x cubed. It doesn't matter which graph you make which. And I'm going to go 4x squared plus 3x. I'm going to graph both of those. Okay, so if we're using this method, what we're trying to now find are the x values of the intersections. That'll help us solve that original equation. So again, you could zoom in. I'm actually going to zoom in a little bit closer here. I'm just going to hit zoom in here and just hit enter. Just so I can get to those intersections a little bit easier. I think I should hit all of them there. And, I'm not going to hit that last one. So I'm going to have to zoom out a little bit. So I'm going to change my window to go all the way out to, let's go out to 5 on the x-axis. And now it should hit all those intersections. There's 1, 2, and, oops, I got to go higher on my y-axis there. Come on. So my y-axis, so I actually don't mind that this is happening because I think it's good for you to see that sometimes your window, it's a little bit of a guessing game. It's okay to have to go back and change things. It just takes a while. And I'm still missing it. But okay, let's go ahead and find these intersections here. Well, this one is 0. You can check that one if you want. But I'm going to find this one right here first. So I'm going to go second, trace. This menu that we keep going to is this calculate menu, which is calculating things on the graph. We don't want a 0 anymore. We want an intersection. So you want to hit number 5. Not like that, though. Try this again. Let's go second, trace, and then you want number 5. All right, now here's what it's going to ask you. It's going to ask you, am I on the first curve that you're dealing with? Well, I can't tell where the cursor is right now, but I can tell that it's on the first curve because of the fact that that's showing that curve up there. So I'm just going to hit enter. Then it says, am I on the second curve? Well, it must be. I don't know where the cursor is, but I can tell that it's on that curve because it's got the equation up there. Plus, this calculator makes it color-coded, so that's kind of nice too. So I'll just hit enter. Now it says guess. I have no idea what that is. I've never seen that before. I'm going to scroll to the left here so I can see my cursor. There it is. And you can always tell where your cursor is once you start moving the arrows by the numbers here. So I'm going to get closer to that intersection right there and hit enter. And look what it finds. -1/2 is one of our solutions then. Now that -1/2 right there is just saying where they meet. That's the y value for both those functions, but they're meeting at an x value of -0.5. So that is going to be one of my solutions. So I'm going to come over here, and I'm going to actually do a sketch of these yet since I haven't. So I've got this cubic guy here, and then I've got this quadratic guy here that is intersecting right there, and then somewhere up there. Okay, it's just a nice little sketch. So we are finding that x value right there, that x value right there, and that x value right there. So we want that guy, we want this guy, we know is 0, and we want that guy right there. Well, we just found out that this was -1/2. And then I could change around my window and go through that same process, and I would find out that this one is 3 halves because we just found it on our last problem. So our zeros are, again, those same 3 zeros, -1/2, 0, and 3 halves. So there's 2 different methods that you could use by graphing. You can do either one, intersections or intercepts. One last thing we're going to do here is see if we can actually factor this thing. Let's get it all on the same side. Now let's factor out an x out of that. So I have 4x squared minus 4x plus 3. Okay? Do not divide by that thing. That's a 0. You can't divide by a variable, you lose an answer. So I'm going to leave that there, and I'm going to try to factor that trinomial that's left. So I'm going to try 2x and 2x. And then we've got, let's see, factors of 3 would be 1 and 3. So I've got 6x and I got 2x. Perfect. If I make that 6x negative and that 2x positive, then I know I have positive 2x, negative 6x. That adds up to that negative 4x that's in the middle, and that's exactly what we wanted. So I'm going to set each of these equal to 0. I get x equals 0 from this one. That's why we couldn't divide by it. We didn't want to lose that answer. From this one, we get x equals subtract 1, divide by 2, -1/2. And then from this one, we add 3 and divide by 2, and we get 3 halves. So this was also solvable by factoring, and we get the same exact zeros that we did when we graphed it.